the field of view. The frequency encoding gradient Gx generates position-dependent frequency signal along x-axis. So in the acquisition of the data, we have to apply frequency encoding gradient. The angular frequency of nuclear spins at x is given by this relation, gamma gxx. The FOV, field of view, represents the size of the MR image. If the size of the MR image along the x-axis is specified by FOVx, then the rightmost spins in the MR images slice have the maximum angular frequency indicated by this expression. Here we put x FOVx over 2. Okay. The spins in the far left, so this gives at this position. Okay. There's the center of the image, and here FOVx over 2. And this position minus FOVx over 2. So at this position, nuclear spins has Raman frequency of this expression. The spins in the far left at this position of the MR image have the smallest angular frequency as indicated by now minus FOVx over 2. So this position. Using the relation omega equal 2 pi f, we can calculate FOVx from the angular frequency difference between the rightmost and the leftmost position in the MR image, which is given by this relation. This relation is obtained by subtracting these two equations. Okay. Then we can identify FOVx in terms of bandwidth omega max minus omega minimum. Okay. The bandwidth defined by BW is difference between maximum and minimum frequency in the MR image, which is expressed by this equation. So here omega max minus omega minimum, and we can use omega equal 2 pi f then bandwidth is f maximum minus f minimum, and we also have this expression. This means that MR signal is the sum of signals with the frequencies ranging from f minimum to f maximum. Okay. the comp function with the interval delta ts becomes comp function with the interval 1 over delta ts when it is Fourier transformed. I already mentioned that. When the sampled signal with the sampling time delta ts is Fourier transformed, which is the same as multiplying the comp function with the interval delta s to the signal, then we have a series of step functions with bandwidth to f maximum from minus f maximum to plus f maximum are produced, separated by now 1 over delta s. We already saw the figure in the previous slide. As a result, if bandwidth as 1 over delta ts is met with to maximum for FPW, then two step functions will not overlap. This also could be seen in the previous slide. The relationship of delta kx, we can get delta kx by differentiating this relation kx. If we differentiating this kx, then gx is constant, so delta ts will become ts become delta ts by differentiating. So we have this relation for delta kx. So delta kx means the size of pixel and the k-space, right, in the along x direction. So this gives the pixel size and the k-space. So we can get this relation because 1 over delta ts is bandwidth, right? So here we can use this relation. Bandwidth is equal 1 over delta ts, then we can have this relation as we use the this relation. And now f of x is given this relation, and delta kx is given by this equation. This relation was seen in the previous slide. Okay. So bandwidth is 1 over delta ts, and compare these two relations, we can get this relation. So this relation establishes a connection along the x-axis, this f of x-axis, with real and k-space pixel size. So this is the pixel size along x-axis in the k-space, and f of x is the image size and along x direction and image space. So this relation gives the pixel size in k-space along x-axis and the image size along x-axis. So the pixel size in k-space is related to inverse of the image size. Okay. the pixel size is calculated. The pixel size in real space, delta x, is f of x over nx. Nx is number of pixels in the MR image. So if we put this f of x here, and using this relationship, kx in pixel size in k-space times number of pixels, then we have size of x in k-space. Then we have this relation. So this gives the pixel size in the image space, and kx is the size of x direction in k-space. Okay. So you can this relationship and gives the relation between the size in k-space and the real space. Now let's see y direction. So far we considered the x direction and k-space and the real space. Now let's consider y direction in k-space and the real space. So how can what can we have in the relation between the size in the k-space and the real space? The phase encoding gradient gy is applied along y-axis before the frequency encoding gradient is applied to read the MR signal. This gradient produces position-dependent phase along the y-axis. The frequency encoding gradient Gx is applied whenever an MR signal is detected. The frequency encoding gradient in each process should be the same magnitude. We use the same slope of the phase encoding gradient to read the signal. However, the magnitude of the phase encoding gradient Gy is changed when obtaining the MR signal and y times. So we have to change phase encoding gradient every time when we get the data by applying the frequency encoding gradient. So totally we have to repeat ny times for ny by ny size image. The smallest phase gradient or step size as given by delta Gy, represented by Gyi, causes the phase difference of 2 pi of ni between neighboring pixels. So we have 256 pixels along y direction. Now let's suppose nx equal ny. Y equal to 56. Okay. So if we use the smallest gradient for phase encoding, Gyi, then this gradient causes the phase difference of ny, 2 pi of ny between neighboring pixels. So the phase encoding gradient causes the phase difference 2 pi of ni between two adjacent pixels. The total phase change between the center and edge is 180 degrees. The center and edge here, pi, and here, there, another edge, minus pi. So total phase difference from edge to edge is 2 pi. Center to edge phase change is pi. Thus we have gamma GYY. Y represents here FOVY over 2. Right? So at edge, right? At the edge here. So here to here, the distance is FOVY of 2. So if we put y, FOVY of 2, then total phase difference is phi. So from this relation, we can get this. And from definition of ky here, if we differentiate this relation, we can have this relation. Here tau is constant, gamma and gy is variable. So if we differentiate this relation, we have delta gy, and delta gy was represented by gyi, okay. So comparing these two relationships, then we can have this relation. This relation gives the pixel size in K space on Y direction, and image size on Y direction is rated by this relationship. Okay, so we compare this and this relation and this relation. We can have this relationships. This relationship establishes a connection along y-axis between real and K-space pixel size. The pixel size is calculated as pixel size in real space, in image space, is delta y, FOVY divided by ny, and y is the number of pixels in the MR image. As a result, using this relation, we can have finally get this relation. Okay. Now the summary summarize the what we discussed so far. Kx and ky was defined by these relationships, and along x direction, the image size is FOVX. So at this point, distance from here plus FOV x over 2, and here minus FOV x over 2. So at this position, the spins at this position have normal frequency given by this relation, and at this point the nuclear spins have normal frequency given by this relationship. So now subtract these two values, or omega max minus omega minimum, and omega 2 pi f, so 2 pi f maximum minus f minimum. This gives bandwidth. Okay. And from here, we subtract these two equations. We have this relation, and we can get this relationship. Okay. According to Nyquist theorem, the sampling rate 1 over delta Ts should be twice of maximum frequency. This is bandwidth in order to avoid aliasing. Hence, 1 over delta Ts is bandwidth. So Kx defined by this relationship. So Kx is given by this relation because we use the sampling time Ts, right? Ts, and the frequency encoding gradient is Gx. If we differentiate this relationship, then delta Kx and here delta Ts. Delta Ts is one of bandwidth, and we use this relation here, we can get this result. And finally we have this relationship. So f of x is the size of image along x direction, and delta kx is pixel size and k-space along x-axis. Okay. And real space, image space, the pixel size is delta x. Is given by f of x divided by nx, pixel size, right? So if you use this one, then finally we get this relationship. So delta x is pixel size, and kx is size in the k-space along x direction. So we can get these two relationship in the x direction. Let's consider y direction. And y direction in the image place the size of the image along y direction is f of y. And if we use phase encoding gradient gy, and then at position y, spins normal frequency is given by this relationship, and the phase angle is omega y time of phase encoding gradient. So with an increment of delta gy at each step for time of tau, the phase encoding gradient is applied along the y-axis and y times. The smallest phase gradient or step size, GRY, causes phase difference of 2 pi over ny between neighboring pixels. We already discussed this one. Okay. So the phase difference between two adjacent pixels is 2 pi over ny. The total phase change between the center and edge is 180 degrees. From here to here, phase change is phi. And from here to here, phase change is minus phi. So totally, 2 pi phase difference. As the phase gradient increase, the phase difference between neighboring pixels increase to value of phi. Okay. So last step. This is last step, right? In the last step, the phase difference between two neighboring pixels is pi. The smallest gradient, the phase difference between two pixels was 2 pi over ny. But the last step, we apply phase encoding gradient NYGYI, then the phase difference between two adjacent pixels is now pi. Okay. So total phase change between the center and edge is ny pi. So totally 2 ny pi. Okay. So for the smallest phase encoding gradient delta gy at edge, from center to edge, so FOVY or 2 phase difference was pi, right? So pi, and then we have FOVY is related to 1 over delta ky. So FOVY represents the image size along y direction in image space, real space. Delta ky is pixel size in k space. And the real space pixel size is related to 1 over ky. So size in the k space along y direction. The signal intensity in the k space is larger in the center, small k. So here, signal is largest, but becomes smaller as k increases. So at the edge, as going to the edge, signal intensity is decreasing. As a result, the MR image's contrast is determined by the center signal, while the details are determined by outer signals. So intensity is largest at the center, so this portion of signal gives the signal intensity, right? Intensity of the image, or image is contrast. If only center signals are used to construct MR imaging by Fourier transforming them, the resultant image is blurred. This gives this image. If you use center signals only, then we have the bright image, because the intensity near center is largest, so we have bright signal, but the details are not clear. Okay? If the MR's image is constructed without the center signal, so we use the outer signal, then the image has sharp edges. So we have sharp edges, but no image contrast, so not bright, because we use the weak signals, weak intensity signals to construct the image. So the image is not bright, but the outer signal gives the details of the image, so we have a sharp image. But if you use the center signal only, then we have bright signal, but the details are not clear. The edge is not clear. We summarized the previous discussion about relation between pixel size in K-space and the real space. This K-space, and the dimension of K-space is Kx and Ky. This image space, or real space, size of image in x direction, f of x, y direction, f of y. Okay. And pixel size in K-space in x direction is related to the image size f of x in this way, and pixel size in K-space in y direction is related to the image size f of y in real space. On the other hand, the pixel size in image space is related to the size in along x direction in the K-space, Kx, and y direction we have the same relationship, similar relationship. The Fourier transform connects the K-space and the image space. The variables in the K-space are spatial frequency Kx and Ky, whereas the variables in the image space are coordinates x and y. Whereas x and y are measured in meters, Kx and Ky are measured in 1 meter. The relationship between pixel sizes in the K-space and the image space are given by this relationship. Okay. The resolution of the image increases if we decrease the image size. Okay, decrease the image size while retaining the number of pixels. So we retained the number of pixels, but if we decrease the image size, then we have the high resolution image. On the other hand, the resolution of the image falls if the image size is raised while retaining the pixel numbers. So in opposite direction, right? So we retain the pixel numbers, but we increase the image size, then we have lower resolution image. Okay. We must increase the number of pixels if we wish to have large image, large FOV with the same resolution. So if we want to same resolution, then we have to increase the pixel numbers. There are some examples regarding what we discussed so far. Example 1. The phase encoding gradient is applied for 0.6 milliseconds. To get an image with a FOV of 10 cm, find phase encoding gradient's increment. We know this relationship, so we want GYI can be obtained this value 2.46 millitesla per meter. Next example. The FOVX of an image is 12.8 centimeter, and the number of sampling is 256. Find Kx, delta x, and delta Kx. Delta Kx, the pixel size in K space, is related to the image size, so we can have this number. And delta x, we have for FOVX, so nx divided nx, then we can have pixel size in Euro space, and the Kx is equal to 1 over delta x, so we can have this value. Next example. The frequency encoding gradient for FOVX equal 10 cm image is 10 millitesla per meter. Find the sampling rate. To find delta Ts. Delta Ts is inverse of bandwidth, right? So from this relationship, we can have bandwidth, this one, so we can have sampling time. This value means 1 over delta Ts, the sampling rate, right? So this gives collecting 6,780 data points each time, the sampling rate. Next example. The image of FOVY equal 10 cm was obtained with NY equal to 156. How long must the phase encoding gradient be applied for the above image if the maximum increment of the gradient is 0.1 millitesla per meter? So FOVY is related to the minimum phase encoding increment is related by this relationship, so we can get the duration time of phase encoding gradient, this value. Next example. The gradient used for phase encoding has a slope of 0.1 millitesla per meter and rest for 2 milliseconds. This tau. At the distance of 2 cm from FOV's center, what is phase change? So So delta phi is this relationship. So we can have 61 degrees. Next example. When the frequency encoding gradient of 5 millitesla per meter was used, the minimum f of x was 20 centimeter. What will the minimum f of x be if the gradient slope is doubled? So first, bandwidth minimum can be obtained this value, and now if we double the phase encoding slope, then image size is decreased to 10 centimeter. It was 20 centimeter, and now 10 centimeter. So f of x is reduced to half by doubling the gradient slope. The f of b is decreased as gradient increase. Next example, what is the minimum f of b of the image we can obtain if we utilize the maximum sampling time 20 microsecond and the maximum frequency encoding gradient 20 millitesla per meter. So f of b is related to gx and the bandwidth by this relationship. So we can have a minimum f of x 3.7 centimeter. Because sampling rate is given, so we can get bandwidth, the inverse of sampling rate, sampling time gives bandwidth. So we can use bandwidth here. Next example. The MR signal's bandwidth is 16 kHz. What sampling rate is necessary to accurately reflect the signal? So Nyquist theorem gives sampling rate should be equal to bandwidth. This is given by Nyquist theorem. So this is 16 kHz, so we can get the sampling time. So sample rate delta ts. This is sample rate, right? This indicates that one data point from the MR signal is sampled every 62.5 milliseconds. So inverse of this gives the sampling rate. So sample rate, this is equivalent to gathering 16,000 data points per second. This gives a sampling rate. Next example. What size is a pixel in the image if nx equal ni to 56 and f of x and f of y is 25 centimeters? So delta x is pixel size in image space. This image size divided by n. So you can get the pixel size is about 1 millimeter. So the pixel size in the image is 1.1 millimeter, both in x and y direction. Next example. the total sample time used was 8 milliseconds. Determine the MRI signal's bandwidth for the 256, and 512 by 512 pixel cases. The bandwidth is inverse of the delta TS, and we know the total sample time, so delta TS can be given by TS over N. So in the case of 256 pixels, we can have 32 kHz. On the other hand, in the case of the 512 image, bandwidth is 64 kHz. In the case of the 512 image, the signal contains more waves with different frequencies. This means that large bandwidth, 64 kHz for the 512 image, compared to the 32 kHz in the 256 image. Thus, the resolution of the 512 image is twice better than that of the 256 image. Next example, the minimum bandwidth is plus minus 4 kHz, and the maximum frequency encoding gradient is 20 millitesla per meter. What is the MRI machine's minimum field of view? Field of view is related to the bandwidth and the frequency encoding gradient by this equation, and the bandwidth is given plus minus 4 kHz, so total bandwidth is 8 kHz, and the maximum frequency encoding gradient is 20 millitesla per meter. So we can get this machine's minimum field of view as 5.9 centimeter. Next example. What is the size of pixel delta x in an image with a FOVX of 150 millimeter and the resolution of 256 by 256? What is the k-space size of pixel delta kx in this image? FOV is given 150 millimeter, and the resolution is given 256. So the pixel size in the image is given by FOVX divided by NX. So we can get pixel size 0.59 millimeter. The pixel size in the k-space is inverse of FOVX, FOV. So we can have pixel size in the k-space is obtained as 0.067 inverse of a centimeter.